for being here into this session and giving us opportunity to continue for this, making like functional composite material session to go for like in the know as along the way, along with this conference. Our first speaker is Masood Ifani Farad from Arizona State University. His topic is properties of carbon nanotube, buck paper, and interface. He's not here, so we will start his talk with his presentation, video presentation. Okay.
Hello, everybody. Thank you very much for this opportunity. My name is Masood Ifani Farad. I'm an assistant research professor with the Mechanical and Aerospace Engineering program at Arizona State University. My talk today is about properties of carbon nanotube bucket paper interface. The first, we'll take a look at basically what we are going to talk about today. Briefly, I'm going to discuss the fabrication procedure for the bucket paper membrane and two-phase and three-phase nanocomposites. Then we will talk about the main goal of this talk, which is about basically the interface around the CNT network and the interface between the bucket paper as when we look at it as a one constituent and the surrounding polymer. The technique that we use is an atomic force microscopy based technique, big force quantitative nanomechanic mapping technique. We look at the heterogeneity and homogeneity of the bucket paper at different length scales, and at the end we are going to look at basically the interface of the interface thickness of the bucket paper. So this slide pretty much shows the a summary of the fabrication procedure. It's basically compression technique that we use for the bucket paper. The bucket paper out of the technique is infiltrated, basically soaked with epoxy resin and under the pressure. The infiltrated bucket paper is used for two different purposes, one for fabrication of the bucket paper films, and the other one is for the fabrication of the three-phase basically nanocomposites. Now, as I said, the technique is atomic force microscopy based because quantitative nanomechanic mapping technique. The technique is pretty much as an established technique. It has some complexities with the calibration procedure, which unfortunately we do not have time to go over the details of it, but the technique is very robust. If it's calibrated very well, it can basically use for basically submicron and nanoscale characterization. The trace and retrace curve is analyzed through a contact mechanic model since the features of this study fulfills the requirement of the DMT model. DMT model was used for the analysis of the results. NCHVA, our test plot 300 and our test plot 500 and TSPSS, the probes were used for this study investigation. So here this slide, the figure A shows the bucket paper before infiltration. When we look at it through a scanning electron microscope, we see pretty much macroscopically and macroscopically, it's a very looks like a very homogeneous structure. It is a basically entangled bucket paper all around this basically structure. Definitely, there are some interbundle and intrabundle porous. So BJH technique was used to characterize these porous. The intrabundle porous were around 30 to 60 nanometer, and interbundle porous were about 80 to 130 nanometer size. After infiltration with the epoxy, through the soaking and pressure, we look at again through the scanning electron microscopy. We see that there are some areas that they look like very well impregnated. We call it dense impregnated zones. These dense impregnated zones they give us a CNT network with pretty much a larger size. Then the other areas that they look like they're loose impregnated zones, and macroscopically, again, it looks like a homogeneous, but on the submicron and nanoscopic scale, definitely doesn't look like much homogeneous. Definitely a technique that can basically explore this heterogeneity would be atomic force microscopy. But these samples first, they need to be polished up to 0.1 micron. And then we look at these samples through optical microscope to basically find the location of the interest. This slender shape, a shiny, basically material is a bucky paper, which is sandwiched between carbon fiber monofilament. So picture A and B, just I put them for the sake of comparison. Picture A is a regular polymer composite, and picture B is a CNT polymer nanocomposite, which is 0.5 weight percent multiple carbon energy. So if you're going to zoom in at this 20 micron thickness slender shape bucky paper, we look at around 9 micron, for example, the deformation profile, and then we do a section box analysis. We'll see that the red curve and blue curve, particularly the red curve, which is a box analysis, larger box around 8 micron by 8 micron, shows pretty much around 3.5 to 4 nanometer deformation throughout the bucky paper, very homogeneous. Meanwhile, the section line, the black line, shows the high level of heterogeneity. The right side of this bucky paper shows completely different deformation profile comparing to the left side. Now, if you look at the histograms over a larger zone of the 20 micron by 20 micron, which pretty much it captures the entire width of the bucky paper. And then we look at the reduced modulus. We'll see that it's skewed to the right with a peak that is around 7 gigapascal, which is close to basically the pure nanoscale reduced modulus of epoxy. The curve, the histogram of the reduced modulus doesn't show a smooth curve, but we are expecting to see a couple of at least peaks for the representative for the interface and CNT, and those happening around 15 to 20 gigapascal and around 30, 35 gigapascal based on the basically stiffness of the probe that we pick. The adhesion is a bimodal, again, skewed to the right kind of a curve with two peaks. One is a representative for the areas that doesn't basically infiltrated epoxy in it, so it's pretty much a void or CNT with no epoxy, and it shows less than 1 nanometer adhesion, and the max, which is around basically between 15 to 25 nanometer. The deformation is a bell-shaped with an average of 2 to 2.5 nanometer, with a handful of the number of the points that shows large deformation. So overall, macroscopically, the reduced modulus of our bucky paper is between 6.2 to 8.2 gigapascal, and adhesion is between 21 to 23 nanometer. Now, when we look at the interface, first we look at the interface of the carbon fiber monofilament and epoxy as a reference. We look at the interface zone. And then for the carbon fiber polymer, we can use both adhesion and reduced modulus or DMT modulus as the channels that we can see the change, basically the variation in the value, and shows the interface. It's interface around 14 nanometer. Now, when we look at the bucky paper, epoxy and carbon fiber, and we zoom on the bucky paper area, somewhere around 2 micron by 2 micron, it's a hill and valley type topology. And then we do the section analysis here, section 6 and 7, passing through the 2D image basic of this bucky paper. We'll see that there are many spikes. Those spikes are representative of the CNT networks. So anything that is highlighted in yellow is a CNT network. The CNT networks have different sizes. Interestingly, the sizes can become classified to two different categories. The first one is a narrow interface, basically network with weight between 30 to around 60 nanometer, which influenced by the size of intra-bonded porous, and the larger, basically, CNT networks, which are between 180 to 150 nanometer, and those are influenced by the interbonded porous. Now, the size of the interface itself is between 15 nanometer, as you see in the picture, up to around 44 nanometer. That has come from our statistical analysis. Now, when we look at the bucket paper itself, and its interface with epoxy, unlike the carbon fiber, here we just only can use DMT modulus as a representative and as a parameter to study the interface. And the interface is much larger, with something between 40 nanometer compared to the carbon fiber and epoxy, which is 13 nanometer. Thank you very much for this opportunity. I would be more than happy to take questions.
Let's thank Dr. Masood. So far, we don't have the question from the audience. If you have anything, you can type me. We can ask directly from Dr. Masood. For this session, our second presenter is Dr. Jin Tang from Guilin University of Technology, China. His topic is preparation of bismuth series visible light catalyst and its mechanism for removing chromium 4 and organophorus flame retardants. Let's welcome Dr. Jin Tang. Dr. Jin Tang, the floor is yours. You can share your screen. Whenever you are ready.
Hello, Professor Tang. Would you like to play the video you provided to us?
I believe she have left for some
Maybe some internet problem. We can play her video instead, I think.
I don't think we have the she have the presentation, but not the video.
Oh. Sorry, Professor, you mean we will wait for Dr. Tang, or we can play her PowerPoint instead?
Yeah, we can play.
I think it is not a video, just some slides. We can go through her slides, maybe.
Let's leave it as a break till the time Dr. Jingtang join us back. If she is not, then we will wait for the next presenter. That will present like 1:20. So let's wait for more couple of minutes. Otherwise, we will move forward to the next presenter.
Okay, if Dr. Tang is not here, we just go through these slides very briefly and until next talker. That's all her PowerPoint.
Our next presenter is Maria Cristina Rigetti. I believe I'm saying her name is in the right way. She's from National Research Council, Institute of Chemical and Physical Processes, Pisa, Italy. Unfortunately, I believe she's not here, and we did not have any of her presentation in terms of video. So let's have a 10-minute break. And after 10 minutes, we will meet with our next presenter.
Hello, Jingkyong. Dr. Jingkyong.
Hello, Professor. I'm here.
Can you play video for Dr. Mari?
Excuse me, for Dr. who? Dr. Lee?
Yeah, Maria. Christina.
We have her PowerPoint, but it does some slides. It's not a live one. So
No, there is voice inside the PPTs. They recorded, so you can play that one.
In this context,
okay, I will share it.
Yeah, thank you.
in this contribution, I will present some results on green composites made of polylactic acid and ecopolymer polyhydroxybutyrate cohydroxyvalerate and the natural fibers from organic waste, with the addition of natural waxes to improve the adhesion between the polymer and the fibers. It is well known that bio-based polymers are more expensive than conventional polymers and often exhibit worse thermal and mechanical properties. To reduce the cost of bio-based materials and obtain suitable properties, a possible solution is given by biocomposites, which represent an ecological and low-cost alternative to common plastics. Natural fibers can be provided also by organic waste. The use of these materials in biocomposites can represent a good method to reduce the cost of bioplastics. Potato pulp is what remains after extraction of starch. The original potato pulp contains a high amount of water, but after drying, the water decreases to about 3%. Dried potato pulp consists mainly of cellulosic fibers, but it contains also starch, pectin, and proteins. The cost of this raw material is low, which makes potato pulp interesting for utilization as a filler or reinforcement for biopolymers. The mechanical properties of a biocomposite depend on the matrix and fiber properties and also on the adhesion between the fibers and the matrix. Unlike poor adhesion characterized biocomposites because natural fibers are hydrophilic and polymers are hydrophobic or less hydrophilic. The poor compatibility can be improved by modifying the fiber surface with physical or chemical methods, but also simple coating can be used. We prepared biocomposites of polylactic acid, which is the bio-based and biodegradable polymer most present on the market, and a polyhydroxyl canoate, in particular ecopolymer polyhydroxybutyrate cohydroxyvalerate with a low amount of hydroxyvalerate units, 1–2 mol%. We added potato pulp. The potato pulp particles size was approximately 200 micrometers. The biocomposites were prepared with the addition of a non-toxic plasticide, acetyl citrate, and the calcium carbonate, which was used in low amount to favor the removal of the injection molded specimen from the mold. And finally, to improve the adhesion, we coated the potato pulp particles with natural waxes, beeswax and carnauba wax. Here, the formulation that we investigated. First, we studied the effect of the plasticide and the calcium carbonate. Then, we added the potato pulp in increasing amounts. And finally, we coated the potato pulp with beeswax and carnauba wax. The specimens were prepared with the mini extruder and the mini injection molder. The processing was performed at 180 degrees for 90 seconds. The temperature of the mold was 90 degrees for the PLA biocomposites and 80 degrees for the PHBV biocomposites. The molding time was 90 seconds. First, we investigated the thermostability by thermogravimetric analysis. In orange, the potato pulp curve. There is an initial weight loss due to water vaporization. The potato pulp appears stable up to about 180 degrees. This thermostability assures that the potato pulp does not undergo substantial degradation during the processing of the biocomposite at 180 degrees. Here are some data on biocomposites of PLA with the potato pulp. The calorimetric curves show that the increase in potato pulp produces a decrease in the glass transition temperature, most likely due to poor adhesion and high free volume at the polymer filler interface. From the area of the cold crystallization peak and the area of the melting peak, we calculated the crystallinity that grows during the cold crystallization and the crystallinity that disappears during fusion. These values were the same, which means that PLA was completely amorphous after processing. As regards the mechanical properties, elastic modulus and tensile strength decrease with the potato pulp amount, which means that there is poor adhesion between the matrix and the filler. So potato pulp acts as filler and not as reinforcement for PLA. The elongation at break decreases with the potato pulp because the filler particles act as stress concentrator. As regards the viscosity of the biocomposite decreases with the potato pulp. This can be due to poor adhesion and the presence of free volume at the polymer fibers interface. When we treat the potato pulp with natural waxes, we can observe that the elastic modulus and the tensile strength increase with respect to untreated potato pulp, as we can see from the arrows. The elastic modulus becomes similar to that of the matrix without the addition of the potato pulp. This proves that better interactions are established between the matrix and potato pulp, which becomes less hydrophilic by the wax incorporation. Elongation at break decreases also after treatment with the waxes. This measurement proves the efficiency of B and Carnauba waxes as coating agents for the PLA-based biocomposite with potato pulp. In these micrographs, we can observe that when the potato pulp is not coated with the natural waxes, there is a well-evident gap around the potato pulp particles. When the potato pulp is treated with the natural waxes, the gap decreases and the fracture surface appears more continuous. We used a model to predict the elastic modulus of these PLA-based biocomposites. This model contains an adhesion parameter which was found lower in the presence of the natural waxes, in agreement with a better adhesion. Also for PHBV-based biocomposites, treatment of potato pulp with B and Carnauba waxes improves the mechanical properties of the biocomposites. The elastic modulus and tensile strength increase, proving a better interface interaction. Also, these micrographs show that the gap between the fiber and the matrix decreases when potato pulp are coated with waxes. Finally, Here, some pots that we prepared by injection molding at industrial scale with the formulation here presented. The study was funded by the European Commission under the project AgroCycle. Thank you very much for your kind attention.
Yes, thanks, Dr. Maria, for her wonderful research and sharing her result with us. Next, our presenter is Vigu Lee, and from the University of Texas at Houston, United States. He's going to talk about the structural design and manufacturing of three-dimensional porous superstructure with additive and subtractive electrochemistry for flexible self-powered electronics, nanoelectrochemical devices, and water purification. So, Mr. Vigu Lee, the floor is yours. You can share your screen whenever you are ready.
Okay. Sorry, let me share my screen. Can you see my screen?
Yes.
Okay, good. Sorry. So, good afternoon, everyone. Thanks for the honor to be here and present our work on structural design and manufacturing of 3D superstructures with additive and subtractive electrochemistry on behalf of Professor Fan. Scientific discoveries must be applied to resolve the real-world problems for making impact. In the coming decades, humans are likely to make a significant shift in the way they live, and we must build more intelligent, sustainable, and applicable materials to support this development and address problems we are facing, including health, energy, environment protection, and the scarcity of water. 3D porous superstructures that are usually referred as two forms, sponges, networks, aerogels, hydrogels, woven fabrics, and papers, have received intensive research interest due to the grand potentials in an array of applications, such as energy conversion, storage and dissipation, sensing of mechanical, chemical, and optical clues, serving as scaffolds for environmental remediation and growth of tissue cells. 3D superstructures have been made of a wide spectrum of materials, ranging from 2D materials like graphene, materials like oxides, polymers. Aggregation issues of 2D materials and preserve excellent physiochemical properties and provide large surface area for active materials loading and reaction. The scaffold structures also enables them to be self-supported with excellent mechanical strength and flexibility, which can be employed as substrate for many devices. In this talk, I mainly focus one type of 3D porous superstructures, which is a nickel foam-based materials. Through CVD, we can obtain graphene forms and utilize it for strain sensors. While electrochemical manufacturing, we can modify the commercial nickel forms as multi-level porous and dendritic nickel forms and make them for supercapacitor and water splitting. Comparing the two types of supercapacitors, the pseudocapacitor stores much higher energy than the double-layer capacitor. However, pseudocapacitive materials are extremely low in conductivity, hence they need to be loaded onto a conductive support. In order to obtain a high capacitance based on the total mass, we need to reduce the mass of the electrode support and enhance the loading of active materials. Thus, we need to develop an electrode support that is highly conductive, lightweight, and provides large surface area. Herein, we employed the Kirkendall effect to create multi-level porous nickel forms to enhance the surface area. We firstly deposit copper thin films on the nickel form branch, followed by annealing at 1000 degrees Celsius. Here, due to the different interdiffusion speed of copper and nickel atoms, micropores underneath the surface start to form and can be observed via cross-sectional view. The formation mechanism of such micropores is the so-called crocodile effect. Then, etching away the surface layer electrochemically, we expose large arrays of micropores on the struts of nickel forms. After employing the porous nickel copper forms as CVD templates, we can readily obtain multi-level porous graphene forms with 2 times enhanced surface area. Following this work, we fabricate tree branch-like microstructures onto nickel forms by electroplating to further enhance the surface area. It is found that the addition of very small amount of copper and chloride ions in the nickel electrolyte can induce the formation of copper-nickel micro-ramifications. The growth of such micro-ramification could be due to the copper-induced anisotropic co-deposition of nickel and copper, as shown in the SEMs. The copper-nickel ramification extend and bridge across the pores to fill in the empty spaces of the nickel forms. Using those nickel forms as the templates, a new type of ramified porous graphite forms can be obtained. It can be clearly seen that the graphitic microtubes will maintain the density and morphology of the diverging copper-nickel branches, and also fill in the large empty spaces between graphitic struts. BET measurements determine that the volumetric surface area has been enhanced by more than 3 times. Next, we glue magnesium oxides onto graphene forms as supercapacitor electrodes and assemble it as flexible or solid supercapacitor and integrated with strain sensors for self-support devices. The integrated device can detect both large and small strains. We can detect the bending of fingers and the pulse of carotid artery. When integrated with an electric nanomotor manipulation systems, the flexible supercapacitor can power the gold nanomotors to trace letters U and T, as shown in the video. This demonstrates the grand potentials of our 3D porous structures. Finally, we utilize our innovative dendritic nickel forms as water splitting catalysts. First, we electroplate ferrite, cobalt, nickel dendrites on the nickel forms, followed by sulfurizing the outer surface to be sulfides. Then, the shell of the sulfides was further electrochemically converted to oxyhydroxides, which is the active materials for water splitting OER catalysts. Our synthesis approach shows several advantages over other conventional methods. First, we directly employ the dendritic nickel form as a substrate and metal source, which can save the synthesis cost and conformably form a thin layer of sulfides on the surface. Second, the in situ transformation from sulfides to oxyhydroxides can guarantee the formation of less crystalline oxyhydroxides that can provide more active sites. As shown in the TM, after the activation, the surface turns from crystalline to polycrystalline. This synthesis also leads to a core shell structure consisting of the alloy metal and sulfides core and ultra-thin active oxyhydroxides layer. Studies show that the sulfides exhibit much better conductivity than oxides and hydroxides. The core shell structure can guarantee the excellent conductivity during the OER test. Then we carry out OER tests over a series of samples. Apparently, the incremental oxyhydroxides grown on dendritic nickel form offers the best OER performance, showing the lowest over potential. Here, we also synthesize 2 samples without adding sulfuric acid and thioacetamide, the 2 key reagents for successful sulfurization. It clearly shows that without the sulfide precursor, the overpotential is more than 130 millivolts higher. If there is no ferrite and cobalt doping, both provide the worst OER performance. exhibiting about 60 to 70 millivolts higher in the overall potential. It has been reported that the doping of cobalt improves the conductivity and assists the electron transfer, which can be observed from the impedance test. Finally, the exceptional performance is also owing to the innovative dendritic structure. Without the dendrites, the overall potential is 47 millivolts higher. Such dendritic structure not only provides the large surface area, but also provides more active sites and facilitate the charge transfer as manifested in the impedance test. Such outstanding OER performance is stable over 18 hours with just a few millivolts change. In summary, we have provided scalable and original materials fabrication approaches to create 3D microporous superstructures, which can be used as flexible supercapacitor electrode support and OER catalysts. Finally, I want to conclude my talk by acknowledging my advisor, Dr. Fan, and other colleagues in Fan Lab, as well as. Thank you.
Thank you so much for your wonderful talk. Since we don't have any question from the audience side, I have one question. Like you have shown like different devices using like copper and iron materials, like with the change of that. I just wondering like so far in comparison, which devices are working better and why you are moving from like different materials? Like what's the motivation of changing? Like is the performance is getting increased or the future prospect in that way?
You mean for the OER for this one or for the for this one? Oh, so for this one, I changed from the copper to actually this one also has copper. First, if we want to grow this kind of dendrites, the copper must be included. But it only has very minor content, so I didn't include copper here. The main functional material for the OER materials is the ferrite, copper, nickel. So I listed these three as the twin metal. So, but in actually it's 4 metals. So the reason I add the 2 metals, a lot of 2 metals, is that the cobalt can improve the conductivity of the whole composite. The ferrite can improve the OER performance. So this is the reason I add these 2. So the overall, the twin metal or the 4 metal structure would be the best candidate for the OER catalysts.
Thank you so much. Thank you so much. Next, we have a presenter, Dr. Gregory P. Holland from the San Diego University, United States of America. He's going to talk about the spider scale as a model system for design of functional protein-based materials and composites. Could you please run the video?
First and foremost, I'd like to thank the organizers for having me. The title of the talk today is Spider Silks as Model Systems for the Design of Functional Protein-Based Materials and Composites. This is work from my lab at San Diego State University in the Department of Chemistry and Biochemistry. I'd just like to get some acknowledgments out of the way up front. Most of what I'll tell you about today involves the top project, that's the Spider Silk project. People who did most of the work, Dr. David Onofree, who's a solution NMR spectroscopist, research scientist in the lab. Most of the work that I talk about today was done by Dylan Stengel, who's a PhD student that's defending in the next couple of months and should have his PhD by the end of the calendar year. And he's been doing mostly solid state NMR of native spider silks and synthetic recombinantly produced spider silk materials. And secondly, Hannah Johnson, who's a newer PhD student in the group who's working on cryo-electron microscopy of spider silk assembly. We have a broad range of undergrads from a plethora of different science departments. I have people from mechanical engineering, zoology, biology, chemistry, biochemistry, chemical physics, amongst others, and lots of collaborators from around the world that are involved in various aspects. The funding agencies that supported the work, primarily the work I'll talk about today, is DoD Army Research Office, but also AFOSR has funded spider silk research in my lab for some time. A little background on spider silk. I'm not sure how many people watching are familiar with spider silk or the field of spider silk or making materials out of spider silk or recombinant proteins from spider silk. So I thought I would say a few things. What makes it significant, I mean, there are many things that make spider silk interesting, but the one that people have studied for a long time is the stress strain curve. So if you've heard about spider silk on scientific literature or even in popular science, the dragline silk or the major ampulate silk, stress strain curves shown in yellow, green, and black for 3 different species of spider, their dragline or major ampulate silk. That's the one that's been studied the most, and that's the one that you've probably heard about if you've heard about spider silk is stronger than steel. It is stronger than steel by weight and tougher than Kevlar. But what I'm going to tell you about here is another type of spider silk called Aciniform spider silk. Aciniform spider silk is what spiders use to wrap their prey. So if you've ever seen an insect in the corner of a web wrapped in silk, waiting for the spider to come and eat it later, the silk it wraps that prey in is called aciniform silk. That silk is not used in constructing webs. It's also used as a minor component in the inner lining of the egg case. What's important to understand about spider silk is it's not just about the commonly studied major ampulate silk, which is an excellent material and one that's been studied quite a bit, but the fact that they make up to 6 other types of fiber materials that vary dramatically in their mechanical properties. They're all strong and tough, but some are highly elastic, some are stiff. So they make a library of fibers from proteins. So back to the aciniform silk, which I'm going to focus on today, you could see its extensibility is over double that of the dragline silk, and it's actually about 50% tougher than dragline silk. So this is a tougher material than the one that you've heard about. Another thing worth mentioning is spider silk has a long history with DoD. It was actually used, Black Widow dragline silk was actually used as the gun sights in World War II. So they couldn't make a fiber that was perfectly cylindrical, 1 micron thin. There was no way to do it at the time. And so they literally had a farm of Black Widows that they would silk. And that's what was used to fabricate the gun sights. Applications moving forward are tremendous. Obviously, the DoD ones like protective clothing, shock-resistant materials. You have your sports. You have your biomedical space, drug delivery devices, suturing materials, grafting for organs, bone grafting, etc. So there's a whole slew of applications if you could harness spider silk in the lab. So the aciniform silk or the prey wrap silk, I'm just going to show you a video here. This is a student collecting it in the lab. These Argiope aurantia spiders react to vibration near the web. And so the video here is just a student vibrating tweezers near the web. You get it just the right frequency. The spider will jump off onto the tweezers and start to wrap it, just like it would be wrapping up a fly or a cricket or whatever it found in its web that it was going to save to eat later. The silk is very thin, so it's only 500 nanometers in diameter. And that's how you know you're getting aciniform silk. The prey wrap silk is only 500 nanometers in diameter. Dragline silk for the same species of spider is about 3 to 4 microns. The tubuliform silk, which is the primary component of its egg case, is about 6 to 8 microns. So it's the finest of the spider silks. The protein sequences look very different than what you see for major ampulate or dragline silk. The dragline silk has a lot of polyalanine, which forms beta sheet structures, and also a disordered Gly-Gly-X region. The sequences of aciniform spider silk proteins look very different. It has short runs of poly-S. It has short runs of SA. There's also these valine-containing motifs. It has some proline, which is similar to the second dragline silk protein. But the most important thing is sort of this toughness here and this high degree of extensibility in trying to understand how the actual molecular structure of the proteins differs between this silk and, say, the dragline silk. We do a lot of NMR spectroscopy in my lab. This is solid state NMR, carbon-based methods. We also do nitrogen-based methods. We do multidimensional, multinuclear stuff. We actually feed the spiders isotopes, C13 and N15 isotopes, in order to label the silk. And what we found with our initial solid state NMR studies is that the silk is highly alpha helical with a low beta sheet content. And so this is unique for a silk in general. So silkworm silk from Bombyx morae is high in beta sheet. The dragline spider silk is high in beta sheet. The tubuliform silk, which is what the spider constructs its egg cases from, is high in beta sheet. So this silk is actually high in alpha helices. And if you remember the mechanical properties, it's also considerably more extensible. So, you know, one thought is that the high population of helical component is part of the extensibility. And you can see we've assigned these different helices here. They're valine rich. Bioinformatics also indicates that they form coil type helices. But what we needed to pin down is there is a fraction of beta sheet. It's low, but there is a fraction present. And our first speculation was that these linker string-like regions, where you have these short runs of serine and these SA repeats, could be forming the beta sheet structures. And that's what's bolded in red. And so we went to molecular dynamics simulations to ask the question, you know, do those regions, do they have a propensity for forming beta sheet? Is that where the beta sheet structures could be forming in the fibers? And so we use a Monte Carlo simulation program called PROFASI. We took those regions that are boxed in red with these short runs of serine and some SA repeating units and put them in PROFASI, did some energy minimization, and what you find as you go through the energy minimization, each star here, as you're going down and minimizing the energy, is captured here in the picture. So go in C1, C2, C3, C4. And what you can clearly see is the progression from these disordered random coils going to beta sheet structures. And you can see as the energy is minimized, the beta sheet structures go up. And so we knew about how much beta sheet was present for the serine and the alanine. We knew how much helices were present, and the numbers seemed to agree. And the molecular dynamics PROFASI Monte Carlo simulations seem to agree. We even went ahead and did the full GROMACS molecular dynamics simulations of the beta sheet structures. And so by combining the solid state NMR, PROFASI, and the GROMACS molecular dynamics, we were able to illustrate that the beta sheet structures arise from the alanine serine rich motifs that are found in the linker region, while those other regions form coil helical structures. And we published this in ChemCom a couple of years ago. We had a nice model of the structure with the coils of the alpha helices coming together in these beta sheet structures. Now, the interesting thing about this material is how it interacts with water. And this is where we're really taking this material now. If you hydrate the material, if you just show water to the material, either high humidity or just spray the material with water, upon drying, the fibers actually fuse together and cross-link. And you can see with solid state NMR, where you track as spun following water wetting, you can see that the alpha helical component and the alanine goes down, and you see a strong beta sheet component coming in. So this is assisted by an increase in beta sheet structure. And we published this earlier this year in Advanced Functional Materials, where we were able to show that some additional linker and string regions form beta sheet following this water wetting. We were also able to measure with a spin diffusion technique in solid state NMR the size of the crystallites, and they are quite small, on the order of about 2 nanometers compared to much larger beta sheet crystallites found in dragline spider silk protein fibers. So in general, a very different material, one that has a unique interaction with water, and we believe that this may be a way to design a new class of bio-inspired materials for a number of different applications, where the goal is to have a highly flexible helical material that you can just treat with water and convert it to this rigid cross-linked beta sheet structure. And so expected applications in defense, but biomedical space as well. And with that, I'll thank you for your attention and enjoy the rest of the conference.
Yes, thanks, Dr. Gregory Holland. If you guys have any questions, please feel free to write me. We will ask directly from Dr. Gregory about your queries. Our next presenter is Dr. Ching Ho from University of Arizona, United States of America. On his behalf, Dr. Chiao Chen is here. His topic is small nanostructure size limited for non-transport within composite film made of single wall carbon nanotubes and reduced graphene oxide shears. Dr. Chiao Chen, you can share your screen whenever you are ready for the presentation.
Okay. Okay. Thank you, sir. I'm sharing the screen here. Sorry,
Sorry, Dr. Chen. Sorry for bothering. I think we can't hear the sound.
Oh, sorry.
Can you run the sound as well? If you can't, we can run this presentation.
There's no sound.
When you are sharing the screen, you can check there is a check for the shared sound
Okay.
on the left bottom.
Okay. Yeah, I will check. Thank you, sir. That's the switch to the share.
How about can you?
Yeah, I see. Right, I see share the sound, right? I see the chat. Okay.
Hello, everyone. This is Qiyu. I'm from the University of Arizona, and today my topic is a small nanostructure size limit for non-transport within composite films made of single-wall carbon nanotubes and reduced graphene oxide sheets. This talk is about the nanocarbon materials. Generally, there are three generations of the nanocarbons. The first generation is the graphene carbon nanotubes. The second is the doping nanocarbons, and the third generation is the carbon-carbon hybrids. Due to the high thermal conductivity of the nanocarbons is used to as the thermal interfacial materials, and because of the high surface volume ratio and flexibilities, the CNTs has good potentials in the supercapacitors. Before our work, the phonon concept should be noted for heat conductions. In semiconductors and non-metal materials, heat conduction is mainly from the phonon. The lattice vibration, lattice thermal conduct has a correlation with the product of the specific heat, group velocity, and the mean free path. In all cases, the thermal conductivities increased as the mean free path increased. In sample preparation, first we mixed the single-wall carbon nanotube with the graphene oxide solutions to have the films. Second, CNT-GO composite films are reduced in chemicals. Third, CNT-RGO composite films are hot pressed for compactions. Our samples are measured with a conventional 1D steady-state heat conduction measurement setup along a strip sample. To minimize the radiation loss, samples are surrounded by the metal foil radiation shield and suspended in a high vacuum. A heater was used to generate temperature difference. Type K thermocouples are used for temperature measurement. Our samples have very small thermal conductance, so the heat loss from the heater is critical now. In this case, we measure the heating power of a heater versus temperature difference with or without the sample. The difference between the two slopes gave us the thermal conductance G sample. We calibrated our setup with 2 miles copper wires with a 2.4% errors at 100K to 400K. Another concern is the thermal contact resistance on both ends of the samples. We used the high thermal conductive thermal grids for both ends. We carried out repeated measurement in one sample with a reduced length. If we plot the thermal resistance R sample versus the sample length, the y-axis interceptions of the plot gave the contact thermal resistance, which is very small. There is a good thermal contact, the 3.7% error to the smallest, the R sample. Here I'm showing you the cross-section SEM images with the pure RGO sheets, 10% weight single wall carbon nanotubes sheets, and 50% weight SWCNT sheets. We can easily find that the increased SWCNT ratio gave us more SWCNT RGO nanocontacts, which means the graphene sheets are divided more. In this table, we observed the increased CNT lead to decreased thermal conductivity and density at room temperature. In physics, more nanocontacts reduced mean free path and lower thermal conductivity. So with many SWCNT RGO nanocontacts in our composite films, the phonon mean free path could be largely restricted by the structure size. Then we can reach the so-called SNS limit. At this limit, the phonon mean free path can be approximated as the structure size, which is the distance between adjacent nanocontacts here. So in-plane thermal conductivity is proportional to the product of specific heat and the group velocity summed up for all phonon models, H equals to CV. In the figure below, this product H is calculated for porous-thin graphene. In the left figure, I'm showing you the temperature-dependent in-plane thermal conductivities for our 7 samples. In general, thermal conductivities increase at elevated temperature, and thermal conductivities can be fitted with the product H curve for porous-thin graphene. Noted, mean free path in RGO samples was not strongly restricted by structure size, and some divergence can be found above 300K. We compared with the other reported nanocarbons. Most samples do not fit H trend except for bulk SWCNT, which is aligned by filtrations and high magnified field. With a strong SNS limit or at SNS limit, SWCNT and graphene may have the same temperature dependency of thermal conductivities, so SWCNT cannot be fully excluded from the measured in-plane thermal conductivity. So here is a summary of my talk today for our single wall carbon nanotubes, RGO composite films. There is a very rare phenomenon with the increased temperatures, the in-plane thermal conductivities of our nanocarbon composite films increased up to the 400K, which is often amorphous materials before. Another thing is that our in-plane thermal conductivities of all samples can be explained by the SNS limit of pristine graphenes. For the future works, the cross-plane thermal conductivity measurements will be done, and electrical conductivities and its correlation with the thermal conductivities will be done too. This work is being supported by the faculty seed grant at the University of Arizona. Also, the SEM analysis was performed by our university's facilities. Thanks a lot. Okay, my talk is done now. Thank you, everyone. Any questions?
Yes, thanks, Dr. Ting Ho. So far, there is no question from the audience side. If you have any questions, please write me. If not, we can move forward with our next presenter, Dr. Smith Roy, from University of Alabama, United States. His topic is simulation of fracture in graphene polymer nanocomposite using molecular dynamics. Chingyuan, could you please run the Dr. Smith Roy presentation?
Sorry, we don't have the video from Dr. Roy. Can we move on? We don't have their video.
Okay, thank you. Then we can wait for like our next presenter. Let's have a 10-minute break. By that time, we will start with our next presenter.
Excuse me, Professor. I think our next talk of Professor Maragoni begins at 2:10.
Yeah, we can start that as we are running little late. So our next talk is from Professor Voltense Zuccolotto from University of Sao Paulo, Brazil. The topic of the talk is like cell membrane covered hybrid nanocomposite for the target photothermal cancer therapy. Can you run the video?
Hi, good afternoon. My name is Professor Voltense Zuccolotto, and I'm here today to talk about cell membrane covered hybrid nanocomposites for photothermal cancer therapy. I am currently a full professor at the University of São Paulo in Brazil. Well, in the last few years, our research group has developed different nanomaterials for application in photohyperthermia against cancer. That includes the gold nanorods, about which I'm talking here today, but we also developed different nanosystems, including the graphene oxide and what we call the gold nanoflowers. It's important to note that all these nanomaterials are theranostic nanomaterials, which means that they are able to perform both diagnosis and therapy at the same time. Okay, so let's talk about the use of nanorods for the combined chemo and thermal therapy against cancer. Initially, we synthesized the gold nanorods using the well-known synthetic route based on CTAB, as you can see here. Depending on the aspect ratio of the nanoparticles of the nanorods, you can tune the electronic absorption in the infrared region. The nanorods produced in your lab were very homogeneous in size and in shape. And we also show here a typical heating and cooling curve exhibited from the nanorods upon irradiation with a laser line in the infrared region, right? Okay. After producing the nanorods, the natural question that came up was how to efficiently deliver the nanorods to the cancer cells. Obviously, we could simply inject the nanorods in the animal models or incubate the nanorods in the cell cultures, but we decided to use a very special type of nanocarriers to deliver the nanorods to the cancer sites. We used the cell membrane nanocapsules, right? And to produce these cell membrane nanocapsules, we first cultivate the cells. In this case, all the nanocapsules were produced using the A549 lung tumor cell. After cultivating the cells, we can extract the cell membrane, and then we co-extrude the cell membranes with the nanorods, allowing the fabrication of these so-called cell membrane nanocapsules. Inside them, we can incorporate the nanorods. But as I said in the previous slide, in this case, we combined the photothermal therapy from the nanorods with the chemotherapy, and the chemotherapy came from the chemotherapeutics beta-lapashone. So beta-lapashone is a very important chemotherapeutic, which is very efficient for cancer cell death. They can become toxic to the cells only inside the cancer cells, so minimizing a lot the side effects. But the problem with beta-lapashone is that this molecule is really insoluble. So using this strategy, we solved the problem with the insolubility of the beta-lapashone, because in this case the molecules were incorporated into the hydrophobic part of the cell membranes of the nanocapsules, right? So using this strategy to manipulate the cell membranes and the gold nanorods, we obtain nanocapsules like this. We can observe in this image, in this TEM image, the nanocapsule produced with the A549 tumor cell membrane, and inside in this image we can observe the presence of 2 nanorods. Obviously, the system is optimized to produce nanocapsules like this, in which much more nanorods can be incorporated into the nanocapsules. Okay, so these nanocapsules can be used to deliver the nanorods to the tumor sites. As we can see here, upon irradiation, for instance, after 10 minutes of irradiation using a laser line in the 808 nanometer of wavelength, we observed that after 10 minutes, the nanoparticles, the nanocapsules, started to destabilize, releasing all the nanorods inside the cells within 20 minutes, right? So again, we show a typical heating curve now using the nanocapsules. We can observe that in a few minutes we can increase the temperature of the nanocapsules by 10 or 20 degrees Celsius, which is enough for the hyperthermia. Okay. We then proceed with the in vitro tests, and initially, without irradiation, we checked about the cytotoxicity of the nanocapsules using the cancer cell line and the normal cell line, HIPAA-RG, which is a normal cell line from the liver. And as we can observe, in terms of reactive oxygen species generation, the nanocapsules are not toxic. But obviously, upon irradiation in the cell cultures, after 10 minutes, we can observe that the combination of the laser radiation and the nanorods from the cell membrane nanocapsules, they promoted a higher amount of cell death, as you can observe in this image. Okay. Well, we also perform in vivo experiments in collaboration with another professor from the University of Campinas, Professor Wagner Favaro. And as we can see, in this case, specific tumors were induced in the animal models. And after the period of induction of the tumors in the animals, a dispersion of the nanorods inside the cell membrane nanocapsules was injected as a single dose intravesically, right, in the animals for the tests. Okay, after the administration, after administering the nanocapsules inside to the animals, the tumor site of the animals was irradiated for 5 minutes with the laser lining in the infrared region. As we can observe here, for those animals treated with the nanorods inside the cell membrane nanocapsules and upon irradiation, we observed a better histopathological recovery from the cancer tissues, from the cancer state. Okay? So, concluding, we have developed a specific targeting system based upon the use of cell membrane nanocapsules, incorporating gold nanorods and beta-lapashone for a combined chemo and photothermal therapy against cancer cells, right? I'd like to highlight very quickly another piece of work from our group in which we used again specific cancer cell membranes to deliver two specific chemotherapies, gemcitabine and the paclitaxel, to pancreatic cancer cells, right? So, with this, I conclude. This is part of my research group, to whom I have to say thank you, because all these guys perform the hard work every day. I also would like to thank our funding agencies, CNPq, CAPS, and FAPESP. Thank you very much.
Yes, thanks, Dr. Rockler. He was talking about the cell membrane covered hybrid nanocomposite for target photothermal cancer therapy. If you have any question, you can write me. Meanwhile, we move forward to our next presenter, Anas Issa. He's going to talk about the development of novel self-centering polyurethane piston-based bracing. Kim-Yong, could you please run his presentation?
Hello, everyone. Welcome to my presentation, which is about the development of novel self-centering polyurethane piston-based bracing. My name is Anas Issa, and this work has been done under the supervision of Dr. Sharia Alam. This work is conducted at the School of Engineering at UBCO in the Applied Laboratory for Advanced Materials and Structures. So for today's presentation, I'm going to go through a few elements. First of all, I'm going to give a quick background about the topic, the materials that are used in this system, I will show some of the experimental results that have been obtained, and finally I will provide some conclusions. So as we all know, earthquakes are a very critical issue that we have to address all around the world. According to the Insurance Bureau of Canada, a total economic losses of a major earthquake in the west coast of Canada can produce $127.5 billion of loss. So eventually this is a huge loss, and we have to take immediate measures to avoid such economic and human losses on the same page. So bracings have been one of the most widely used techniques to resist lateral loads, mainly earthquakes and winds. These bracings come in different shapes and different configurations, but for conventional ones there have been many problems and issues where we see different types of failure modes, such as in-plane and out-of-plane buckling, or the failure in the connections. So these type of failures can cause huge, again, economic losses. That means we have to replace the system and the adjacent members, and in many cases we have to demolish the building. What we tried to develop here based on that is what we call self-centering polyurethane piston-based bracing. So from the name you can tell it's a mechanical system that has a piston moving part, and it utilizes the polyurethane as a material, and also it has the ability to self-center itself after the loading. So the good aspects about this system that it is light in weight, it has some good self-centering behavior, and it is relatively cheap to construct. So as we can see, there are few simple parts that constitute the system. We have two halves of steel tubes, two ends, inside which we have two pieces of polyurethane cylinders, and in the middle, centered between them, a steel piston that moves in both directions to apply tension and compression on the system. So as I mentioned, mainly the two components or the two materials that contribute into the building, into the system here is simply polyurethane and steel. And as we all know, steel has some good strength, ductility, durability, and stiffness characteristics that is utilized to provide the overall stiffness integrity of the system. On the other hand, the main component that takes the load is the polyurethane. So this material has a high load and bearing axial capacity. It also has some strong bonding properties. It performs well under heavy loads and impact loads, and also it has very good self-centering behavior, which is very critical in seismic applications. So first of all, we started, after fabricating the system, to apply some different loading protocols. We used the universal testing machine to install the specimen between the two heads of the machine, and we attached the needed strain gauges and LVDTs to measure different performance parameters, such as strains and loads and so on. So as you can see here, this is an actual picture of the system, the fabrication and so on. After installing the specimen, it becomes as one piece or one system here that, as I mentioned, is installed in the machine. Different loading protocols have been applied, different cycles, and it applies both tension and compression to the system, and we try to increase the amplitude of the displacement to see how much capacity it can take. And as we'll see later, that it has considerable amount of strain deformation ability with very good self-centering behavior. So we first started with around 15 millimeter, and then we moved to 22 millimeter, and in some cases we applied 25 millimeter, which imposes 10% strain to the polyurethane. And as we can see, we have some good energy dissipation behavior, some also very good self-centering ability. And as I mentioned, the system was very stable, and we repeated the tests several times with different rates, as I will show in the next. So here we apply different strain rates for the different loading protocols, as I mentioned. It is considerably noticeable here that with increasing the loading rate, starting from the original rate all the way up to 100 times the original rate, which was 1 inch per minute. So we started from 1 inch per minute, 2 inches per minute, 5, 10, 50, and 100 for both loading protocols. And as you can see, that with the higher the rate, actually we can observe higher maximum force or axial force capacity, and also some increase in the energy dissipation capacity. If you look at the figure at the left here, you can see a comparison between the original rate and 100 times the rate, so the two extremes, and you can clearly see the difference between the two behaviors in terms of actually in some extent better behavior, higher energy dissipation, higher load carrying capacity, and as I mentioned before, here you can see at 10% strain demand, the system still went back to its original shape, and the residual deformation were relatively small. So in conclusion, the system, as we have seen, perform well under tension and compression. It has a very good self-centering behavior. It also has some high strain capacity. Compared to other materials, this is actually very high. Some other materials like shipping or alloys can take 6 to 8% before it actually yields. So this is reaching 10% is actually high. It is very light in weight, so compared to other systems such as buckling resistant braces or typical or conventional bracings, this is very good advantage. And also it is relatively cheap alternative, so this material is becoming very popular, and it is increasing its popularity over the time, and been used in many applications such as load barriers and impact kind of isolators and so on. So we try to actually bring this material into the seismic or civil engineering applications to serve as a competitive for other available systems. I would like to mention here also that there are different studies that now we are trying to conduct on this system. We will try to provide some pre-compression to the system to see how the energy dissipation capacity might increase and so on. So hopefully we can share these results with you in the coming conferences and workshops. So thank you all for your time and attention, and if you have any questions, I would be more than happy to answer them. You can send me your questions into my email, which I will provide in the conference platform. Thank you again, and have a good day.
Let's thanks our presenter. Our next presenter is Ms. Nafisa Abdurrahim Yaqub. She's going to talk about evaluation of impurities, concentration with the hot probe method, and optical constants of nanostructured titanium dioxide embedded polymer thin films. Jin Young Zo, could you please run her presentation?
Hello, this is Nafisa, and I will talk today about evaluation of impurities concentration with hot probe method and the optical constant of nanostructured titanium dioxide embedded in polymer thin films. Here's the outline of my talk. First, I will introduce the topic of my research. Then I will explain the reason that why this research is carried out. Then I will show the objective preparation of the polymer nanocomposites, results obtained from experiments. After that, I will conclude my talk. I will start with the definition of the conducting polymer. Most of the polymer are insulator, but with doping and mixing that with metallic nanoparticles, it starts conducting electric charge. The distinct change in the properties of the polymer nanocomposites is influenced by the type of integrated nanoparticles, their size, shape, and their concentrations, and the interaction with the polymer matrix. This kind of polymer nanocomposites are widely used in the polymer solar cell in medical application, artificial muscles, fabrication of electronic device, and rechargeable batteries and sensors. The new development of technology requires fabrication and growth of artificial materials that present strong and broad absorption with high carrier mobility and appropriate energy levels. Applying these type of materials for various electronic devices require characterize the semiconductor by different parameters such as the type of semiconductor, the impurity concentrations, mobility of the charge carrier, diffusion the carrier mobility and concentrations for the polymer nanocomposite have different methods like 4-point probe and whole effects measurement. The main problems in the application of these methods to the thin films parameter measurement are in the measuring device and sensitivity and in the complexity of the specific sample preparation. In my research work, I have used the new hot probe method that based on the thermal excited majority free charged carriers, which are translated from the hot probe translated within the semiconductor from the hot probe to the cold probe. The setup of the hot probe experiment is shown in this figure, where the hot probe is connected to the positive terminal of the voltmeter, while the cold probe is connected to the negative one. In applying cold and hot probe to the N-type semiconductor, a positive voltage readout is obtained in the meter, where for P-type semiconductor a negative voltage will obtain. The hot probe experiment can be used by three various methods. For type of semiconductor and thermoelectric voltage depends on temperature, where we can calculate the Seebeck coefficients, and the majority charged carriers concentration and the dynamic parameters of the semiconductor material. In my research, I have used the hot probe method to determine the type of semiconductor and evaluate the impurity concentrations. In this research work, we will study the majority charged carriers concentrations of the PMMA composite with the anatase phase of titanium dioxide nanoparticle thin films and calculating the optical constant of the thin film. To prepare the nanocomposites, we have used the casting method to prepare the polymer nanocomposite of the PMMA polymer composite with the anatase nanoparticles in the different 5 concentrations. All the thin films have characterized via XRD technique and FECM. XRD pattern consists low peaks intensity of the titanium dioxide at around 25 and 14 degree, and from FECM image, it's confirmed that the homogeneous dispersion of the nanoparticles in the polymer matrix are observed in the samples. The linear optical properties of all thin films are studied from the absorption and transmission spectra, which are recorded using spectrometer in the range of 119 to 1100 nanometer, and the band gap energy of these nanocomposites are calculated in addition to the photoluminescence of the thin films. Here I will show the important and major results in brief. Transmission and absorption of the PMMA nanocomposites. This figure shows that the transmission, and this one for the absorption of the PMMA anatase nanocomposites for different weight percentage of anatase in the thin films. The transmission figures demonstrate that the transmittance decreases with increasing the amount of the titanium dioxide, and the decrease in the transmittance in the visible region is very high. The absorption increases with increasing the weight percentage of titanium dioxide in the films and have almost the same profile as a function in the wavelength. The direct and indirect optical band gap energy of the PMMA anatase are calculated from transmittance spectra using talk boards in this equation, where M is a constant, depends on the type of the optical transition. When M equal 2, it's the best value for the fitting for allowed direct transition, and M equal half is for indirect transition. It seems from the table that the pure PMMA thin films have 5.05 electron volt energy band gap for direct transition and 4.88 electrovolt for indirect one. By adding anatase nanoparticles, there is an overall decrease in the band gap energy. The decrease in the band gap might be due to the splitting of each level into many levels, equal to the number of the interacting atoms according to the energy band theory. So the bands come closer or overlapped, which reduce the energy gap between the levels. The fluorescence of the PMMA anatase thin films was done at room temperature and excited the thin film with the 200 nanometer wavelength, and the spectra of the emission is shown in this figure. There is 4 peaks of emissions observed at 202 and 423 nanometer, 632 nanometer, and 815 nanometer. The emission is weak for the low concentration of titanium dioxide and increases with increasing the weight percentage of anatase in the PMMA polymer. This peak is corresponding to the band edge emission. The second one, this one is cut for saturation and is the origin luminescence from the titanium dioxide nanoparticles. And this peak at 632 nanometer, which is in the green emission, is because of the recombination of the photo-generated Hall and signali ionized electron in the valence band. By using the hot probe method, the type of the charge carrier was examined by recording the voltage change with increasing the temperature, as in this figure. By increasing the temperature, the voltage was positive, which means the thin films show an N-type semiconductor. Secondly, in this experiment, we have estimated the impurity concentration, and it was done for 0.80 weight percentage of anatase nanoparticles in the PMMA at temperature of 200 Celsius. And as in this figure, and the time between the initial and the steady state was 20 seconds, and we get maximum voltage 0.3 millivolt. The impurity is calculated using this equation, where R is the function of the heating temperature, Ni is intrinsic charged carriers concentration at normal temperature, delta P is the additional charge carriers, appears to be thermal excited charge density, and we get impurity concentration is equal to 4.1 multiplied by 10 to power 52 per centimeter cube. And here is the conclusion of my work. My talk: the direct and indirect band gap energy of the PMMA anatase thin films is decreases with increasing the weight percentage of anatase nanoparticles in the thin films. The emission of the thin films is weak for the low concentration and increases with increasing the weight percentage of the anatase in the PMMA polymer. And the PMMA anatase nanocomposite showed an N-type semiconductor, and the charge carriers impurity concentrations was estimated by using hot probe method. Thank you for your attention.
Let's thank our presenter, Dr. Nafisa. If you have any question, you can write me. We can ask directly from the presenter. Our next presenter is Dr. Long Yu from Hozhong University of Science and Technology, China. His topic is ferroelectric nano-crack-based nanoelectrochemical switches for the memory of the complementary logics. Dr. Zhou, could you please run his presentation?
Hello everyone, welcome to my presentation. It is an honor to share and discuss with you here. I am giving this report on behalf of Professor Long Yu. The topic of our report is ferroelectric nano-crack-based nano-electromechanical switch for memory and complementary logic. I will give my presentation from 3 aspects. Faster speed, miniaturization, high density, and low power consumption have become important goals pursued by electronic devices in the future. In order to meet the booming development of information technology, it is urgent to study low-power devices. In the past few decades, device feature size have been continuously reduced under the guidance of Moore's law. However, as the size is reduced to a few nanometers, leakage current becomes a big problem. Static power consumption cannot be ignored, and CMOS has a minimum operating voltage limit due to Boltzmann limitation. In recent years, various CMOS technologies have been proposed to develop low-power devices. Among them, nano-electromechanical switch and piezoelectric device are two devices that have been hotly discussed. AM switch is an electrically regulated mechanical switch with characteristic size on the order of nanometers. It has an abrupt on-off switching process and thus can achieve ultra-low sub-threshold swing. In addition, in principle, it provides zero leakage current and high on-off current ratio. However, it also has some limitations, such as complex preparation process, large control voltage, and material and structural failure. Piezoelectric oxides utilize polarization switching to construct functional devices by voltage control, offering great advantages in non-volatile, scalability, and energy efficiency. To date, diverse piezoelectric devices have been developed and extensively investigated, such as piezoelectric capacitor memory, piezoelectric field effect transistor, piezoelectric tunnel junction, and so on. In this work, we will introduce an emerging beyond CMOS technology, piezoelectric nanocorrect device. This device combines the advantages of NEM switch and piezoelectric device. Previous studies have shown that under cyclic electric field, cracks with nanoscale widths can be induced in piezoelectric single crystals. Interestingly, the crack can open and close with the piezoelectric domain switching, which can act as a mechanical switch. However, we find that the locations and states of cracks are very random, and it is difficult to accurately control them. These problems limit their continued in-depth application. In our previous work, we have realized the precise control of crack locations and crack states by designing a braid structure. This is due to that the appearance of the cracks are regarded as the release of the elastic energy produced from domain switching, and this is related to the electric field distribution. The crack is easy to be induced in the location with high electric fields. Through designing the device patterns, non-uniform electric field distributions can be achieved. In addition, we have found a complementary switching characteristic of double cracks. In this device, one crack is open, while the other one is always closed. This phenomenon resembles the complementary CMOS technology. Thus, we can construct complementary logic based on the nanocrack devices. However, there are still some crucial issues to be tackled for this new technology. For example, the scaling performance of this piezoelectric nanocrack device is lacking, and It is desired to condense the memory and logic functions into a single device level, which can be applicable for logic in memory. With these questions in mind, we launched the following further research. Firstly, we introduced the single crack-based memory device. This device is comprised of ferroelectric oxide and metallic thin film on top of the oxide layer. The film is etched into parallel strips with a gap length Lg. The voltage Vg is responsible for inducing the crack formation and control the crack switching. We applied the triangular voltage waveform to induce a crack. After the crack is induced in the oxide layer, it will extend into the metallic thin film and reversibly switch in the film. VDS serves as the reading voltage to detect the resistance, which is decided by the state of crack. When the crack is open, a nanoscale air gap is formed, and the current path is cut off, leading to a high resistance state. The operator Vg enables the closing of crack, and the current path recovers, corresponding to a low resistance state. Thereby, we can find that it is a non-destructive without process here. The SEM image shows the morphology of the crack. This work, we select PMNPT single crystal as the ferroelectric material and MNPT as the metallic thin film. From the IV curves, we can find that our device shows a high on-off character ratio even at a small VDS, and also presents a non-volatile characteristic. In order to confirm the metallic context at the closed state, we compared the on currents before and after the crack is induced. Through compare the black and blue lines, the small difference indicates the metallic context even after the crack is induced. Also, our device shows good stability and voltage pulses and a wide working temperature range. Next, we investigate the scaling down of our device. Through simulation analysis, we found that the operating voltage can be effectively reduced by reducing the gap length Lg. Interestingly, sub 1 volt operating voltage can be obtained with Lg reduced to 100 nanometers. Then we fabricated the devices with different Lg. When Lg is 500 nanometers, the operating voltage average 3.5 volts, while when Lg is 300 nanometers, the operating voltage can be reduced to about 2.5 volts, which are consistent with the simulation results. This figure summarizes the operating voltages for different Lg. With Lg decreasing, the operating voltage reduces quickly. We also illustrate the minimum single device structure design, which is potentially scalable down to dimensions with only 2 domains, since a crack is mostly possible induced along the domain boundary. In order to confirm the stability of operating voltages of our device, we have carried out cyclic tests of switching loops and conducted the statistic analysis. Specifically, the forward switching voltages are extracted from the loops, and we record the counts of different voltages. We find that the distribution of the forward switching voltages follows a Gaussian distribution, and these results confirm the stability of operating voltage. Also, we extracted HRS and LLS from the repeatability tests, which show a high on-off ratio for different devices. Our device also shows good retention both for on-state and off-state. Then we demonstrate the logic gates based on the complementary switching of double cracks, as shown in Figure 1. The basic structure is the same as the previous one for memory logic, but for memory application. But here, we focus on the correlation of two cracks induced in the separated thin-film zones. Under the application of VG, one can always find that one crack is open and the other one maintained closed. The underlying mechanism is the complementary distribution of electric field. The SEM image clearly shows that the two cracks have opposite states. Under the IV curves, we can find that when crack 1 is open, the crack 2 is closed, confirming the complementary characteristic. In order to construct a logic gate, we add an insulating layer and a top metal layer in the device. The insulating layer is used to isolate the output signal from the input one. This is the top view of the circuit. V1 is applied on the bottom electrode to control the crack switching. When V1 is positive, crack 1 is open and crack 2 is closed. Thus, Vout will be connected to V3 electrode. On the contrary, when V1 is negative, crack 1 is closed and crack 2 is open. Vout is connected to V2 electrode. This is one fabricated device. This is the output characteristic of our fabricated inverter logic, and this is the circuit diagram. When input voltage is high, the output voltage is low. This is one out of two multiplexer. When this cell is assigned to 0, Vout outputs the signals of VA, and when this cell is set to 1, Vout is consistent with VB. We also demonstrate AND and OR logic. This is a half-adder logic based on two devices. This is a summary performance of our device. It has a high on-off ratio and a wide working temperature range. This is a calculated low rate energy. It should be noted that some features are theoretically predicted, which needs further experimental investigation. As a summary, in this work, we have condensed the memory and logic functions in a single piezoelectric nanocorrect device. A reliable metal-like context is confirmed through comparing the conductance before and after the crack is induced. A zero offset leakage current is obtained due to the ideal cut-off characteristic of the crack. Thus, a high off-cut ratio has been demonstrated. At sub-micrometer scale dimensions, the low operating voltages have been observed, and we have constructed logic gates based on the complementary switching characteristic, and a variety of logic gates such as NOT, multiplexer, and an OR logic function have been demonstrated. Thus, we believe that the nano-crack-based devices offer a new energy-efficient hardware platform for logic in memory application. This is our report. Thanks. That's all.
Thank you so much, Dr. Longyo. If you have any question, you can write me. Otherwise, like, we can move with our last but not least presenter, Dr. Elizabeth Carlo Leti Cardoso from the Institute of the Poscioso and Energeticals and Nuclears from Brazil. So, Dr. Jingozo, could you please run the recording for the Dr. Elizabeth?
Hello, everybody. My name is Elizabeth. I'm going to present a study of efficiency of ionizing radiation, PBAT, PLA blend, reinforced field bioeggshell. My co-workers in this paper were Declare, Sandra, Luis, and Ademar. Polymers are employed for numerous purposes in different industrial segments, generating waste amount increasing gradually. We have here details of residential municipal solid waste composition, where we can see the plastics is about 11% of the residential municipal waste. Large-scale production consumption of plastic has created several problems worldwide. Reduction of our research increased the carbon dioxide discharge in the atmosphere and environmental pollution caused by waste plastics. Top 10 single-use plastic found European beach by number of items found. That we can see cigarette butts about 22% of waste. Sustainability. Sustainability, we have some relevant definitions as bioplastics or biopolymers, bio-based and biodegradable materials. Chicken eggshell, various uses for chicken shell that can be seen here in the figures. Composition of an eggshell, very important for us, is the composition of chemical composition of eggshells. Calcium carbonate, calcite range for 94, 97, 3 to 45% organic matter. Sustainable use of research associated to pollution prevention. It will be fundamental for next generation. Most of conventional feedstock, polypropylene and polyethylene, are general fossil-based and are being accumulated in environment as solid wastes. An alternative approach to reduce this problem is using POA, polylactic acid. It is a biodegradable plastic polymer, but it has some properties, good properties, biodegradability, biocompatibility, high strength, high mods, but they are unsatisfactory for some application, elongation, impact strength, shock absorbing, toughness, etc. To solve this PLA deficiency, we have to blend it with other biodegradable polymer. Here we choose a PBAT. It is a polybutylene adipate quaternary phthalate, and it is completely biodegradable and flexible. This is our objective. Materials that we used, we use the PBAT PLA blends, as they have a poor interface adhesion due to their different glass transition. Then we have to use ionizing radiation to change the interface in the bulk of both polymers. As compatibilizer, use PLA E-beam radiated 200 kilograms and PLA gamma radiated 200 kilograms. We use PLA, PBAT, and calcium carbonate from avian eggshells that they were prepared from white chicken eggshells to have it fine. Eggshells 5 reduced to 125 microns. Materials, we prepared some 4 samples from PBAT and from PBAT 50% of PBAT POA, and they were prepared in a twin screw extruder, temperature profile 130 to 145, and screw speed at 50 RPM. Characterization we perform using the GSC, TG, HER, FTR, X-ray analysis, and tensile and elongation at break. For GSC, we have a figure 1A melting curves for analyzed samples, 1B melting curve for sample constituents. Here in this table, we have the results for peak and fusion enthalpy. And for TG, we have figure 2A TG for samples, 2B TG for constituents. Here we have in this table onset and set and weight loss. HER, FTR, we have FTR, the first graph, 3A, FTR of samples, 3B, FTR of constituents, and 3C, FTR of PLA irradiated. XRD, X-ray diffraction analysis, we have for A, TRX diffractograms for samples, and for B, GRX diffractogram for samples constituents. As conclusions, we have the main objective of this paper was the study of efficient of two compatibilizing agents, aiming to provide a better miscibility between PBLT-POA blend, 50-50 reinforced BioHL, 125 microns particle size, 15 PHR, 5 and 10 PHR of PLA E-beam, and gamma radiate, 200 kilograms were used as compatibilizing agents. Evaluation comprised GSC, TG, HER, FTR, XRD, and tensile elongation at break. Sample contained PLA gamma radiate as compatibilized proved to be more effective than samples containing PLA E-beam radiate according to mechanics, according to tensile strength. My acknowledgement to BASF, IPEN, at her, Natural Works. Thanks. This is my email for forwarding correspondence for further some doubts that you can have. Thank you.
Yes, thanks our presenter, Dr. Elizabeth, who was talking about the study of efficiency of the ionizing radiation of in PBAT, PLA band reinforced with biological eggshells. She was our last presenter for this session, as well as for the last presenter for this conference too. In the end of this, all these amazing sessions with all these presenters, I would like to pay my gratitude and thanks to all presenters, speakers, session chairs, the volunteers who was working with us to make this event successful, and especially your help as a listener to make this event successful. Hopefully, we will see each other next year physically at the UCLA. Till that time, I want to say thanks and bye to you all. Thank you so much.